66 million years ago, something roughly 10 to 15 kilometers wide slammed into what is now Mexico's Yucatan Peninsula at nearly 64,000 kilometers per hour, ending the reign of the dinosaurs and wiping out about 75% of every species alive on Earth at the time. For decades, scientists have known where it hit, how big it was, and roughly when it happened. What they never definitively knew was exactly what kind of space rock it actually was. On July 17, 2026, an international research team finally answered that question, using a technique precise enough to read chemical fingerprints preserved in a thin layer of clay buried at 5 separate sites across Europe. Their conclusion? The object that ended the age of dinosaurs was a CO chondrite, a specific, exceptionally rare class of meteorite, so uncommon that it makes up only a sliver of the roughly 5% of Earth's meteorites, already classified as carbonaceous chondrites. As one of the researchers put it plainly, being struck by a projectile this rare from this far away really does underscore just how genuinely unlucky the dinosaurs were. But this discovery does more than just satisfy a decades-old curiosity about what, exactly, ended the Cretaceous period. It's quietly reshaping one of the most widely accepted theories about how the impact actually killed so much life on Earth in the first place, shifting the blame away from a mechanism scientists have favored for years and towards something considerably less obvious. Every fact in this video comes directly from the peer-reviewed paper itself and the researchers' own public statements. No dramatization needed, since the real story already involves a 6 billion-year-old rock, an almost impossibly precise detective process, and a scientific theory quietly being rewritten in real time. To understand why identifying this asteroid's exact composition took so long, and why it matters so much now that scientists finally have an answer, you first need to understand exactly how difficult a puzzle this always was. The asteroid responsible for the Cretaceous Paleogene extinction event, often called the KPG extinction, was first definitively linked to the impact back in 1980, when physicist Luis Alvarez and his son, geologist Walter Alvarez, discovered a thin, unusual layer of clay at the geological boundary marking the end of the Cretaceous period, enriched with unusually high concentrations of iridium, an element rare in Earth's crust, but considerably more common in asteroids and comets. That single clue eventually led scientists to the Chicxulub crater itself, a massive, buried impact structure roughly 180 kilometers across, hidden beneath the Yucatan Peninsula and the surrounding Gulf of Mexico. The Alvarez discovery was itself a genuinely dramatic moment in the history of science, arriving at a time when the leading explanations for the dinosaurs' extinction were considerably less dramatic. Gradual climate change, shifting sea levels, or slow evolutionary decline were among the more commonly favored theories at the time. The idea that a single, sudden, catastrophic impact from space had ended an entire geological era initially met significant skepticism from much of the scientific community. It took roughly a decade of additional research, including the eventual identification of the Chicxulub crater itself in the late 1980s and early 1990s, before the impact hypothesis became the broadly accepted dominant explanation it remains today. That history is worth remembering, because it's a useful reminder that even now, well after the basic "an asteroid did it" question has been thoroughly settled, plenty of genuinely important details about exactly how and exactly what kind of object remained open for further discovery decades later. But knowing that an asteroid hit, and even knowing roughly how big it was, is a very different problem from knowing exactly what kind of asteroid it actually was. Here's the core difficulty. When an object this massive slams into Earth at tens of thousands of kilometers per hour, the impact generates enough heat and pressure to vaporize almost the entire asteroid on contact. According to researchers involved in this newest study, only an absolutely minute fraction of the original object survived the impact in any recoverable form, meaning scientists have never had anything resembling a genuine intact fragment of the Chicxulub impactor to directly examine. Everything they have been able to determine about its composition has had to come from painstakingly reconstructing faint chemical traces left behind in the geological record, rather than studying the object itself. For years, the most useful of those faint traces came from elements like iridium and, more recently, ruthenium. Elements whose isotopic ratios, the specific proportions of slightly different atomic versions of the same element, can serve as a kind of chemical fingerprint distinguishing different broad categories of asteroids and comets from one another. But even those methods came with real limitations, capable of narrowing down the impactor's likely general category without ever pinning down its more specific, precise classification. That's exactly the gap the July 2026 study, led by researcher Georgi Makatadze and published in the journal Science Advances, was specifically designed to close. The research team, drawing on scientists from the University of British Columbia, along with institutions in Paris, Brussels, and Vienna, used a technique called nickel isotope analysis, applied to samples of the KPG boundary clay collected from 5 separate sites scattered across Europe, including a particularly well-preserved boundary layer at Stevens Klint in Denmark. Nickel isotopes offer a more finely detailed chemical signature than the iridium measurements originally used back in the 1980s, capable of distinguishing between considerably more specific categories of meteorite, rather than simply confirming that an extraterrestrial object was involved at all. The result of that analysis was remarkably precise. The nickel isotope signature matched specifically and consistently across all 5 sample sites. The chemical fingerprint of a CO chondrite, formerly known as an Ornans-type carbonaceous chondrite, named after the location in France where the first known example of this meteorite class was originally found. As Dr. Philippe Claes, a visiting professor at UBC who worked on the study, explained, carbonaceous chondrites of the Ornan class are genuinely nothing like the typical meteorites found in most museum collections. Carbonaceous chondrites overall account for only about 5% of all meteorites ever recovered and classified on Earth, and CO chondrites represent only a small fraction within that already uncommon broader category, making them, in Clay's own words, some of the most primitive and least studied objects currently known anywhere in the solar system. It's worth explaining a bit more about why isotope ratios, rather than simply examining an object's overall chemical makeup, offer such a precise classification tool in the first place. Different categories of asteroids and meteorites formed under distinctly different conditions during the earliest days of the solar system's history. Different distances from the sun, different temperatures, different exposure to various forms of radiation, and those differing formation conditions get subtly encoded into the precise ratios of different isotopes or slightly varying atomic versions of elements like nickel, ruthenium, and iridium. That encoding survives remarkably well even after an object has been almost entirely destroyed, meaning researchers can still reliably classify what kind of object left a particular chemical trace behind, even when, as in this case, virtually nothing of the original object physically remains. Finding a match this consistent across 5 independent geological sites, gathered from different countries, using samples originally deposited by the same single ancient event, gives researchers genuine confidence that they aren't simply looking at a localized anomaly or contamination at any one particular site. This new nickel-based finding didn't emerge in isolation either. It directly built upon, and meaningfully sharpened, an earlier 2024 study led by researcher Mario Fischer-Götte, which had measured ruthenium isotope ratios at KPG boundary sites in Denmark, Italy, and Spain. That earlier research had already concluded the impactor was very likely a carbonaceous asteroid, rather than a purely rocky silicate-based asteroid or an icy comet, and specifically suggested it had originally formed somewhere in the outer solar system, beyond the orbit of Jupiter. Christian Koberl, who co-authored both that 2024 ruthenium study and this newer 2026 nickel isotope paper, has been directly involved in tightening that identification considerably further, from a broad, carbonaceous asteroid from somewhere beyond Jupiter, down to a specific, narrowly defined meteorite subclass, a CO chondrite, most likely originating from either the outer reaches of the asteroid belt near Jupiter, or from a more distant, debris-rich region even farther out in the solar system, possibly extending as far as the Kuiper belt. That progression, from a general, it came from somewhere far away conclusion in 2024 to a precise, specific meteorite classification in 2026, represents a genuinely significant tightening of scientific understanding, achieved through 2 independent isotope-based techniques that reinforced and refined each other's conclusions across roughly 2 years of continued research. Here's where this discovery moves from an interesting historical footnote to a finding that's actively reshaping one of the dominant theories in extinction science. And it comes down to one specific, unusual chemical property of CO chondrites. For decades, the leading explanation for exactly how the Chicxulub impact managed to kill off roughly 3/4 of all species on Earth centered on sulfur. The impact site itself sat atop sulfate-rich rock formations in the Yucatan Peninsula, and the dominant hypothesis held that the collision vaporized enormous quantities of that sulfate rock, along with any sulfur contained within the asteroid itself, injecting massive amounts of sulfur dioxide into the atmosphere. That sulfur dioxide, the theory proposed, would have converted into reflective sulfate aerosols high in the atmosphere, blocking out sunlight on a global scale and triggering a sudden catastrophic cooling event, an impact winter severe enough to collapse food chains and ecosystems across the entire planet. That sulfur-driven cooling mechanism had genuinely strong supporting evidence behind it for years, which is part of why it became the dominant explanation in the first place. Geological evidence from the KPG boundary does show clear signs of a sudden, severe global cooling event immediately following the impact, and sulfate aerosols are a well-understood, well-documented mechanism for exactly that kind of rapid atmospheric cooling, observed on a smaller scale following major volcanic eruptions here on Earth throughout recorded history. The theory wasn't a guess pulled from nowhere. It was built on a genuinely reasonable, evidence-supported mechanism that simply assumed the impactor itself carried a meaningfully high sulfur content, an assumption this new CO chondrite identification directly challenges. CO chondrites throw a genuine wrench into that specific mechanism. As Clays explained, this particular class of meteorite contains dramatically less of several volatile elements compared to other, more commonly studied meteorite classes, specifically including lower concentrations of carbon, zinc, water, and critically, sulfur. That doesn't overturn the broader idea that the Chicxulub impact caused a severe sunlight-blocking global cooling event. The geological evidence for that basic outcome remains solid. What it does do is make it considerably less likely that sulfur carried within the asteroid itself was the primary smoking gun driving that catastrophic cooling, since an object this depleted in sulfur to begin with would have contributed meaningfully less atmospheric sulfur dioxide than earlier models, built around more sulfur-rich meteorite types, had generally assumed. That leaves a real, still developing question. If it wasn't primarily sulfur from the impactor itself, what actually did most of the damage? The emerging answer, supported by this new finding alongside separate converging research, points toward fine, pulverized silicate dust rather than sulfur-based aerosols, as the more likely primary driver of the extinction event's severity. A separate 2023 study published in Nature Geoscience specifically found that extremely fine micrometer-scale silicate dust, generated by the sheer force of the impact pulverizing enormous quantities of solid rock, could plausibly have remained suspended in Earth's atmosphere for as long as 15 years, a genuinely long-lasting sunlight-blocking haze, independent of whatever specific sulfur content the asteroid itself happened to carry. Together, these three separate converging lines of research, the 2023 dust persistent study, the 2024 ruthenium isotope study, and this newest 2026 nickel isotope study, are gradually shifting the scientific consensus away from sulfur as the dominant killing mechanism and toward this considerably less sulfur-dependent, dust-driven explanation instead. It's worth being precise about exactly how settled this revised picture actually is. This isn't a case of one single study overturning decades of established science overnight. It's a case of multiple independent research teams using different isotopic techniques and different geological sample sites, all converging on a broadly similar revised picture over the past several years. Exactly the kind of gradual, evidence-based scientific correction that tends to indicate a genuinely well-supported shift in understanding, rather than a single, isolated, potentially premature claim. It's worth stepping back and asking why identifying the precise meteorite class behind an extinction event that happened 66 million years ago deserves this much careful, ongoing scientific attention today. Because understanding exactly what killed off 3/4 of all species on Earth isn't purely a historical curiosity. It directly informs how scientists model and prepare for the genuine, if extremely rare, possibility of a future large asteroid impact. If fine silicate dust, rather than sulfur content specific to a particular asteroid type, turns out to be the dominant driver of catastrophic post-impact cooling, that meaningfully changes how researchers should model the potential climate consequences of a future impact involving an asteroid of a completely different composition. A future impactor made of ordinary rocky material, rather than a rare carbonaceous chondrite, might still generate a comparably dangerous quantity of fine atmospheric dust, even if it happened to contain considerably more sulfur, or considerably less, than the object that struck 66 million years ago. Getting the actual killing mechanism right, rather than over-relying on one specific event's particular chemistry, genuinely matters for how seriously and accurately scientists can model future planetary defense scenarios. This connects directly to real, currently active planetary defense efforts. Organizations like NASA's Planetary Defense Coordination Office rely heavily on impact modeling to estimate the likely consequences of various hypothetical asteroid strikes, informing decisions about which potentially hazardous objects deserve the most urgent tracking and monitoring attention, and what kind of deflection or mitigation strategies might be necessary if a genuine threat were ever identified. A modeling framework that incorrectly weights sulfur content as the dominant factor in determining an impact's climate severity could meaningfully misjudge the actual danger posed by an approaching object with a different non-carbonaceous composition. Correcting that underlying assumption, using solid evidence gathered from the one confirmed mass extinction causing impact scientists actually have detailed data on, represents a genuinely practical, forward-looking benefit tied directly to this otherwise historically focused research. There's also a deeper, genuinely fascinating implication buried in the specific type of object identified here. CO chondrites are considered some of the most primitive, chemically unaltered materials remaining from the earliest days of the solar system's formation, roughly 6 billion years ago. If the Chicxulub impactor really did originate from the distant outer reaches of the solar system, possibly from a region as far out as the Kuiper Belt, then the object responsible for one of the most significant extinction events in Earth's entire history traveled an extraordinary distance, across billions of years, before finally colliding with our planet at precisely the wrong possible moment for the dinosaurs. As Clays put it, being struck by such a rare, distant projectile genuinely underscores just how unlucky the dinosaurs specifically were. A chance encounter between Earth and a rare visitor from the far edges of the solar system, arriving after untold ages of drifting through space. It's also worth noting, honestly, that the exact origin point of this specific asteroid remains genuinely unresolved even after this new identification. Researchers have narrowed the likely source to either the outer regions of the asteroid belt near Jupiter, or a more distant, debris-rich region, extending potentially as far as the Kuiper Belt. But pinning down the precise original location with any greater specificity than that currently sits beyond what existing evidence can support. That's an honest, appropriately cautious limitation on an otherwise genuinely significant scientific advance. So, here's where this stands right now. On July 17th, 2026, researchers confirmed through detailed nickel isotope analysis of boundary clay preserved at 5 sites across Europe that the asteroid responsible for ending the age of dinosaurs 66 million years ago was a CO chondrite, one of the rarest classes of meteorite ever recovered and classified on Earth. That identification builds directly on a 2024 ruthenium isotope study that first pointed toward a carbonaceous outer solar system origin, tightening that earlier, broader conclusion into a specific, named meteorite subclass. And because CO chondrites carry unusually low concentrations of sulfur compared to other meteorite types, this same finding is actively reshaping how scientists understand the extinction event itself, shifting emphasis away from sulfur-driven cooling and toward fine, long-lasting silicate dust as the more likely primary killing mechanism. What remains genuinely unresolved is exactly where in the solar system this specific asteroid actually originated. Somewhere in the outer asteroid belt near Jupiter, or somewhere considerably farther out, potentially in the Kuiper Belt, remains an open question current evidence can't yet definitively settle. And the broader shift in understanding exactly how the impact translated into a global mass extinction, how much fine dust, exactly how long it lingered, and how it interacted with whatever sulfur genuinely was released, remains an active area of ongoing research, building on this newest identification rather than closing the book on it entirely. The real question isn't whether an asteroid ended the age of dinosaurs. That's been settled science since the 1980s. The real question is exactly how it did so. And this new identification of precisely what kind of rare, ancient visitor from the far reaches of the solar system was responsible is bringing scientists closer than ever to a complete, accurate answer. If you want to be here the moment researchers pin down exactly where this rare asteroid actually came from, or finally settle the dust versus sulfur debate for good, subscribe to the channel and turn on notifications. Because when that research comes out, we'll break it down here with the real data, not the invented version. One rare rock, 66 million years. A mystery that's finally getting its most precise answer yet. Whatever new evidence eventually pins down this asteroid's exact point of origin, this discovery already stands as a genuinely elegant piece of scientific detective work, reconstructing the identity of an object that was almost entirely destroyed on impact, using nothing but faint chemical traces preserved in clay, gathered from 5 sites across a continent more than 66 million years after the fact. Thanks for watching.